let's talk about magnets. Magnets, come on, pen. Magnets. All right, so essentially there's two main types of magnets that we deal with. There are ferromagnets. Ferrum is the Latin word for iron, so these are iron-like magnets. And we would often call these like permanent magnets. All right, so let's start with talking about them. Today, you were experimenting with magnets, and those ferromagnets, the actual iron magnets that will hold their charge. I shouldn't say charge, hold their magnetism. Sorry. All right, so if you take a compass and you move it around this thing, what you'll notice is that the compass points away from north and into south. Okay, and depending where you move the compass around, what you will find is that you get a magnetic field set up that looks like this. Okay, right around the whole magnet. Always out of north into south. Okay, and it looks like that. So that's the first note to make, is that magnetic fields orient out of north and into south. Out of north and into south. Now there's a whole bunch of different types of metals or alloys that can be magnetized. Someone mentioned rare earth magnets, so neodymium and so on, or your other alnico and that sort of thing. These are all in the class of ferromagnets. Okay, so anything that can be permanently magnetized is a ferromagnet. You test magnetic fields with a compass, and you draw your field lines based on what your compass, how your compass points. Okay. So let's just have a look at a few more field orientations here, just to see what they're gonna look like. So if I add in a couple of more bar magnets in various different configurations, what we'll find is we can map these fields out and get a sense of what the fields look like. It's a lot easier to do this with magnets than it would be to do with, say, electric fields, although the shapes of the fields end up being somewhat similar. And you'll see what I mean in a second. So out of north and into south. Get this kind of a thing happening here. So the analog in terms of the electric field would be if you had a positive and a minus. Please don't get the two confused. Magnetism and electricity, although related, are not the same thing. They are not the same. Okay. Although one can cause the other. We'll see that in a minute. So that's what you would get there. And just to continue this idea, if we were to have two norths pointing towards each other, well, the magnetic fields would interfere, and if you were to put a compass right in the middle, it would be equally repulsed away from north, okay, from either north, and you would get actually an area of no field right in the middle, so you get this kind of a thing going on. Which is kind of neat looking. I guess. So you get this kind of a thing going on. Alright, so, you know, it's as long as you just remember that rule, that fields point out of north and into south, it's kind of easy to imagine what these fields would look like, and draw them accordingly. Just imagine putting your compass anywhere around in these areas, and whichever way it would point, that's the way your field lines are going to aim, okay? And sometimes you see all these arrows on there, but that's really unnecessary. Just follow the way it's going. Okay, any questions? Okay, so the next thing we'll talk about with ferromagnets is the concept of domain theory. How a magnet actually makes its magnetism is like a really deep rabbit hole. And so to kind of keep it somewhat simple and understand the basics of magnetism, we go with domain theory. Now, domain theory is quite elementary, and I think if you were a quantum physicist, you would laugh at this. But for our purposes, this is going to work. Get a little bit more into what's actually happening in a sec here. But so what we imagine is that the inside of all matter, whatever it happens to be, is full of domains, okay? These are electromagnetic domains, if you want, okay? And each domain acts like a tiny magnet. So, if you were to have a non-magnetic material, what you would find is that the domains are randomly oriented, okay? They just sort of point in all different random directions. If you imagine that each of these domains is like its own little magnetic region, the net, sum of all of these would work out to zero magnetism. Okay? So this is non-magnetic matter. Okay? The domains cannot be aligned in non-magnetic matter. In a ferromagnet, though, you have something different going on. So if I just copy this, move it all at once, I can. So there we have no magnetism, but in a ferromagnet, you can have all of these domains line up. Now, they might not be perfectly aligned, but the more perfectly aligned you get them, the stronger the magnet will be, okay? So some of the more modern magnets would have more of their domains, perfectly aligned. So if we were to say do this, to get this to happen, and then the key piece is align the domains and have them stick in an aligned position, okay? If that happens, okay, we get the field coming out here. Now what we've done is we've created this into a permanent magnet, so long as those domains stay aligned, okay? You can cut the magnet in half, and you'll just make two magnets, a north and a south end, right? And so on. So how do you align domains? You have to do that by applying an external magnetic field. So when we remagnetize our magnets, okay, that little machine we put them in creates a magnetic field, and it's actually done by electricity, but we'll get there eventually. And what that does is it aligns the domains in our ferromagnets, and they stay aligned. Over time, these domains will drift, and your magnetism will decline over time as these start to randomize themselves, okay? Yeah. So external fields align the domains. And if the domains stay aligned, okay, we have a ferromagnet. So these domains here, right? These imaginary little magnetic regions. Well, at their very, at their most basic, you have to remember these areas are made up of atoms, and atoms have electrons going around them. And it's the quantum properties of the electrons, and specifically the spin of electrons, and whether or not these spins, I'm going to say sum to zero or not, is responsible for magnetism. Now it sounds like voodoo, but that's about as good as it's going to get for this stuff right now. Again, the source of the magnetism is the motion of electrons. All right, so certain things can de-align or demagnetize a bar magnet. So one thing is concussion, so hitting it, smashing it. So if you hit these things, hitting magnets can demagnetize them. I don't want that color, I want this color. Hitting, dropping, etc. can help de-align the domains. And heating can also cause this to happen. So every magnet, every type of metal that is magnetic, every type of magnet material, yeah, ferromagnetic material, has a temperature at which it will demagnetize. And that is called the Curie temperature. Oh, my writing's getting terrible. Called the Curie temperature. Okay. So as you excite the atoms, they jiggle around a lot, and at a certain specific temperature, shoop, all of these magnetic fields de-align, or all these magnetic domains de-align. I'm sure we call these domains. Okay, so that's domain theory, and that's how ferromagnetism works. So the next type of magnet is a paramagnet. So paramagnetism. And these are the main types. There's some other stuff like, what is it, ferrimagnetism, anti-ferromagnetism, I think. But let's just stick to the basics. I think that's right. That might not even be the right word I just said. I'm not sure exactly. But again, not something we're going to commonly run across. So in these things, the concept is very similar. There are domains still in here, but the domains do not remain aligned. Okay? So you'll probably notice that your fridge, oftentimes, unless it's like an aluminum fridge, which some are now, you can't stick any magnets to them, but old school, like steel fridges, are only magnetized when you bring a permanent magnet near them, right? So you can stick a magnet to them, but you cannot stick other paramagnets to them. So they do not remain magnetized. So their domains will only line up for limited amounts of time, right? While there is another permanent magnet brought nearby them. Let's say so this would stick to that metal, right? But then if you took it away, this would cease being magnetism or magnetized. Okay, so domains only aligned. While an external field is present. So what this leads us to understand then is with iron, there's essentially two types of iron. There's hard iron, which is capable of becoming ferromagnets, so that's ferromagnetic. And then there's another kind called soft iron, which is actually paramagnetic. So all iron has magnetic character, but whether it can become permanently magnetized depends on which of the two classes of iron it falls into. Natural magnets, like, what do we call those things? Lodestones, right? Or magnetite or so on. They have minerals in them full of ferromagnetic materials, and they actually become magnetic when they are molten. Okay, so you can imagine really hot, like lava, and the Earth's magnetic field will force these things into pointing in a certain direction, right? And then they cool, right? These lava flows cool, and then you have a rock, essentially, that is magnetized in line with Earth's magnetic field. Over time, due to like continental drift and so on. Due to continental drift, you know, stones with magnetic fields in them can like move around. But since they've essentially frozen in this orientation, what you can do is you can either map whether the Earth's magnetic field has moved or whether the land has moved in relation to the Earth's magnetic field based on the way these are pointing. Like for instance, if you know this were found somewhere where you know the magnetic field of Earth was this way, right? You would know that either the magnetic field changed or this stone has moved. So that's used in geology often. Okay. Ancient people found found lodestones, and compasses were invented, you know, thousands of years ago. I don't know the exact date, but compasses have been used for a very long time. So there you go. And then the last type of magnetism we need to talk about is called diamagnetism. And this is like mysterious to me, but basically putting any material in a very strong magnetic field will cause it to show some magnetic character. Okay, even living things. If you put a living thing in a strong enough magnetic field, you can actually get it to do weird things like levitate. If you search around the net, a levitating frog, you will actually see a frog in an insanely strong magnetic field floating around. And strawberries. Yes, I've also seen strawberries. True. And then the last thing is the Tesla. And this is the unit of magnetic field strength. And so basically this unit is arrived at, if you, and we'll get there eventually, this is a little bit beyond the scope of what we're talking about, but if you take a 1 meter long wire and you run a 1 amp current through it, that moving charge will react to a magnetic field. So if you place a magnetic field around here, if that magnetic field is 1 Tesla, then there will be 1 Newton of force on this wire. Okay, so basically what we have here is we have newtons per amp per meter. And this will make more sense when we talk about electromagnetism in the future. But basically, you can measure any magnet, its magnetism, in terms of Teslas.